Professor Marcel de Jeu from Leiden University, and he will be giving a talk on convergence structures on lattices of operators and bicommutant theorems. This is part 1 of his presentation, and I believe part 2 will be given by his student in the afternoon. Thank you, Professor. Please go ahead.
Thank you, Wenji, for the introduction, and thank the organizers for the invitation. Can you hear me? Do you see the screen?
Yes,
well, I presume you do. My presentation also is on a different monitor, so I'm looking sideways. Hope it doesn't look too impolite. I'm about to report on joint work with Björn de Rijk, who was a master student of mine in 2012, and Yang Deng, who will deliver part 2 today. My talk has 2 aims. The first is that I want to advertise vector lattices and vector lattices of vector lattice algebras of operators in particular as objects of study. And I want to show you around in the toolkit that we have developed for their study. It will become apparent that there's certain natural questions that you need to answer before you can actually begin. So the structure of the talk is as follows. I start with a motivational part from bicommutant theorems, which is what Yang Deng will be speaking on this afternoon. After that, I will hopefully have convinced you that we need a toolkit to study vector lattices and vector lattice algebras of operators, and then I shall actually start filling this toolkit. The first thing that I shall then consider are locally solid topologies on vector lattices of operators, and then more generally convergence structures on vector lattices of operators. We have a very naive approach of convergence structures, so I hope that Jan Harm van der Wal will not reproach us for that. After that, there will be very brief on convergence structures on vector lattice algebras of operators. And then I hope to be able to conclude, if there's enough time, with a little more information on orthomorphisms. And let me already advertise Yang Deng's lecture at 1:30 Tunisian time this afternoon, who will speak on bicommutant theorems, only part of his work on that. So here's the start with the motivational part. We start with a upgraded bicommutant theorem for Hilbert spaces, as I like to call it. We have a complex Hilbert space, and we take a star invariant subset of the bounded operators. And then the following 3 subsets of the bounded operators are equal. You take all these operators that leave all A invariant closed subspaces invariant. So this is what is generally called the alglat of A. You can take its bicommutant, so you take the commutant and then the commutant again. And this is also equal to the closure in the weak operator topology, or equivalently in the strong operator topology of the star subalgebra that is generated by A, which is now the algebra generated by A. And the equivalence between 2 and 3 is generally known, of course. It's known as the bicommutant theorem, but it's also these sets are also equal to the one under the first bullet. And this is actually very interesting if you're doing representation theory, which is what I like to do in an ordered context. So for me, it is very natural to ask whether there's an analog of this upgraded bicommutant theorem or any bicommutant theorem in the context of vector lattices. So let me just present one analog that there exists. There will be question marks, which are actually the motivation for this talk. So here's some notation and terminology that I need anyway. So E will always be a Dedekind complete vector lattice. We have the order bounded operators on E, which are the regular ones. We have the order continuous operators on E. I prefer this OC over the somewhat nondescript normal. We have the orthomorphisms on E, which are the band preserving order bounded operators on E. since orthomorphisms are automatically order continuous, we have this chain of inclusions. And now I have to distinguish various types of commutants and then also of bicommutants. First is that you can take a set of linear operators and then you can take its commutant in the orthomorphisms. So you take all orthomorphisms that commute with all guys in this set A. You can play the same game when you consider the commutant in the order continuous operators or in order bounded operators. You can vary on this, of course, but these two will be sufficient for our needs here. And I should also have the need of what we call the star property of a set of linear operators, namely that together with every invariant band under A, its disjoint complement is also invariant. And this is the analog of what you have in Hilbert spaces. If you have a star invariant set of bounded operators on it and a linear subspace is invariant, then its ortho complement is also invariant. And that is what we prefer to have in this context. But now we have to require it. But it's easy to come by such sets that have the star property. For instance, every group of lattice automorphisms has this star property. Okay. Now here we have an upgraded bicommutant theorem for vector lattices, but it is incomplete. So here we have our setup, E is dedicated complete. We have our subset of the order continuous operators that has a star property, for instance, a group of automorphisms. And then the following three subsets of the order continuous operators on E are equal. Well, the first one is it's all-glad again. So you look at all A invariant bands, and then you look at all order continuous operators that leave all A invariant bands invariant. So this is precisely as for the Hilbert space. And now we take a bicommutant, but in a shrewd way. First, we take the commutant of A in the orthomorphisms, then we have a subset of the orthomorphisms, and then we take the commutant of that subset of the orthomorphisms in the order continuous ones. So it's a bicommutant, but not by taking the same bicommutant twice. These two are always equal. This we know. A Freudenthal spectral theorem is behind that, and the interesting part is the third bullet. Now in the Hilbert space context, you have the say strong operator topology closed star invariant subalgebra that is generated by A, and now I would very much like to have something similar here. So I would like to have some vector lattice algebraic structure, whatever, which should be closed in some convergence structure and minimal, should be generated by A. And the task, the challenge is to determine what should be here. What convergence structure should you take, and what is the vector lattice algebraic structure that you should put here? And this we would like to know in this particular case, but also in other contexts where Yang Deng will speak about this afternoon. But just to give a sample of a possible answer in the case where E is atomic, then this was found out by Björn in 2012. What you can take under Buddha 3, what is the answer, is the smallest order closed unital subalgebra that contains A that is also an ideal of the order continuous operators. This is a whole mouthful, but you can think of this as the unital band algebra that is generated by A. And that is the answer. So it should be closed in order convergence. That is the what you need here. Okay. And if you look at this slide still, there are many candidates that you could put here as a convergence structure. So the first question is, what natural convergence structures do you have on vector lattices of operators at all? And how do these relate? So let me speak very loosely on convergence structures. For me and for Yang in our papers, we have a very naive definition of convergence structure. So it's just a non-empty collection C of pairs where the first entry is a net and X is the limit, quote unquote, of the net, such that with every net and every limit, also every subnet with the same limit is in that convergence structure. And the constant nets together with the limit are in that convergence structure. And these are, of course, very easy to come by. You have all nets that converge in some topology on E together with the limits. You can have all order convergent nets with the limits, or all unbounded order convergent nets with the limits, or all, well, whatever you think of, or whatever behaves reasonably with respect to taking subnets will fit the bill. I already mentioned on the previous slide unbounded order convergence. Maybe I should recall what this is. This has been attracting quite a bit of attention recently. So we have a net in a vector lattice, and we say that it's unbounded order convergence to 0 when all its truncations are order convergent to 0. So it's a kind of, I think of it as a kind of local convergence. It's convergent in every principal ideal. Well, here are some questions that you could ask. So suppose that you have a net that converges UO to 0 in the vector lattice, which is also the order bounded operators. Is it then true that if you let this net act on a fixed element in E, that this net that you get in E is also unbounded order convergent to 0? Or maybe the converse is true, or maybe both are true or both are false. It's a very natural question that you ask yourself when you start working on these things. And here's another issue that you run into when you are looking at algebras. So, for instance, that you have a net of operators that is unbounded convergence to S, and another that is unbounded order convergence to T. Is it then true that this net is unbounded convergence to the product? So is this convergence, is multiplication simultaneously continuous with respect to this convergence structure? And here are some answers. Well, the answer to both questions 1 and 2 are negative, but they are both affirmative when all the T alphas are in fact orthomorphisms. The morale of these two papers is that the orthomorphisms are very well behaved. Also in the third bullet, this is not true, not even when you require the S alpha and the T beta to be order continuous, but it is always true when these guys are orthomorphisms. Okay. And as I already said, when you start thinking about these bicommutant theorems, you need such basic facts on your desk to be able to work with them before you start taking on the real problems, so to speak. And we decided to make a systematic study of these issues and fill the toolkit that we felt is needed to do this. And I can assure you that when you set your teeth into these problems, these are not homework exercises that you just solve on half a sheet of paper when you need the answer. Some of these are serious things to consider, even though the questions and the answers are very easy. And what I shall be talking about in the remainder of this talk is this toolkit basically, and some results that we found along the way. And the motivation behind all this, the bicommutant theorems, that will be the topic of Yang Deng's lecture at 1:30. And of course, we also hope that this toolkit that we have filled is of use not only for bicommutant theorems, but more generally. Okay, so let's start with the convergence structures that are topological. I do it more generally, not just on the order bounded operators on E, but order bounded operators from E to F, where F is also data incomplete. And I'm aiming at a linear topology on this vector lattice of order bounded operators. And how can we get a topology at all if there are no norms available or something? Well, this obvious idea is that you introduce a strong linear topology on this space of operators that corresponds to this linear topology that you are given on F somehow. So what you require is that all point evaluations that send T to T evaluated at some fixed point X, these should be continuous for all X in E. That is not entirely what you want still, because we're working with vector lattices and you want continuity of vector lattice operations in this topology. So we are looking at a locally solid linear topology that has this property. And that is not so difficult to do. We sorted this out under the most minimal hypothesis. And here's the easy case, the easy general case, so to speak. So we have two vector lattices. F is Dedekind complete. E need not be here. And we suppose that we have some Hausdorff locally solid linear topology on F somehow. And then there exists a unique topology on the order-bounded operators, which is called the absolute strong operator topology corresponding to TOF, which has the property that a net is convergent to 0 in this topology precisely when the absolute values of the net acting on a fixed point converge to 0 in the topology of F. So this is what you like introducing the strong operator topology on the bounded operators between two bounded spaces. Exactly the same, but there's a modulus here. And then everything is as you would like for every for every x. This point evaluation is continuous. Sorry. This is an Hausdorff locally solid linear topology. And it solves the problem in a minimal way. It is the weakest locally solid linear topology, such that the point evaluations are continuous. Sorry. Okay, so we have this this construction, and there's a nice remark that we could make here. If E and F are the same, so we're looking at the bounded operators from E to itself, then the restriction of this absolute strong operator topology to the orthomorphisms is simply the strong operator topology. That is the kind of most natural definition. And the reason is that we have this equality for orthomorphisms. That is a side remark. Now we want to take special kinds of topologies for these TOF. For instance, here to notions of topologies that are around. We have an O for order Lebesgue topology, which is a locally solid linear topology such that order converges implies convergence in the topology. And the name goes back to the dominated convergence theorem due to Lebesgue. Similarly, we have a UO Lebesgue topology when unbounded order convergence implies convergence in the topology. It is always true that the UO Lebesgue topology is an O Lebesgue topology because order convergence implies UO convergence. And there's a general procedure which I will not go into, but if you have an O Lebesgue topology TOR on the vector lattice, then you can cook up what is called the unbounded topology that corresponds to it. And this is then a UO Lebesgue topology. And it's also true that the vector lattice admits at most one Hausdorff UO Lebesgue topology. And if it does, then we denote it by TOR. Okay, now we suppose that F admits Hausdorff UO Lebesgue topology, and then we take an order convergent net in the order bounded operators, then also the absolute values converge to 0, and then we evaluate pointwise it is convergent to 0. And because this topology is O Lebesgue, it is then true that this convergence holds in F. But that is precisely the convergence criterion for nets in this absolute strong operator topology. So the morale of this story is that if F admits a Hausdorff O Lebesgue topology, then this absolute strong operator topology that corresponds to it is a Hausdorff O Lebesgue topology, and then you can turn the crank and cook up the unbounded topology corresponding to it, which is then a Hausdorff UO Lebesgue topology. And for people interested in these Hausdorff-Euler topology, this is a reason for joy that when you start with the Hausdorff-Euler topology on F, you have a Hausdorff-Euler topology on the operators from E to F. Actually, you can be a little bit more ambitious and see how the equivalences are when F and E coincide. Here's a theorem. Either all of E, the orthomorphisms, and the order-bounded operators admit this desired Tohead topology, or none does. And the implications are we can now already partially understand, because from 1 to 3 I just demonstrated on the previous slide. From 3 to 2 it's a general principle that because the orthomorphisms are an ideal in the order-bounded operators, then any Tohead topology on this guy restricts to a Tohead topology on the orthomorphism. So this is a general principle. And from 2 to 1 you have to work a little bit harder, and I hope to be able to spend some time on that. You show that they have the isomorphic universal completions, and you can exploit that fact. Okay. For any conversions, if you take any vector lattice E, then the order-bounded operators are also vector lattice. So you have the convergence structures that correspond to order convergence and unbounded order convergence in this vector lattice, and possibly also in this Tohead topology. But also you have the strong counterparts, as it is indicated, for instance, here for the order convergence. You say that the alpha is strongly order convergent to T when it is so pointwise. And likewise, you have a strong unbounded order convergence if they converge UO pointwise. And similarly for this Tohead topology. So with every where am I? Something what is happening here? Let me just lose the page down. Yeah, here I am again. Sorry about that. We have uniform and strong versions of convergence structures. And all in all, we have 6 convergence structures on the order-bounded operators from E to itself. And there are 6 times 6 is 36 conceivably implications between these convergence structures. And we sorted them all out. Here's the table that contains all implications. Let me tell you how to read the table. So here we have a 0 in the cell SOO. And this means that there exists a net in some LOB of E that is strongly order convergent, but not order convergent. And here, the value here 1 means that an order convergent net of operators is always pointwise order convergent. And these are essentially the only applications that are valid here, because if you let me turn the page down, yeah. Because it's always true that order convergence implies UO convergence, which implies by definition Tohead convergence. And this means that if you have a 1 somewhere in the table, you can derive other ones from it. And the actual work is finding examples that validate the zeros, so that certain implications are not true. And well, you may argue, well, there's no reason to expect that there are any interesting implications between these convergence structures at all. And so this is, in the end, it is true for the order-bounded operators, but for the orthomorphisms, things are much better. For instance, in the orthomorphisms, it is true that unbounded order convergence and strong unbounded order convergence coincide, and the same goes for this Tohead and strong Tohead convergence. And for people who are familiar with this UO convergence, you can check this in the case of measure on LP spaces, because then you know how these things relate to almost everywhere converges and converges and measured, and you see it happen actually, that these two are equal. Okay, well, this is the implications between the convergences. We also sorted out what the relations are between the how it is with the continuity of the multiplications. So here we have a right multiplication with a fixed operator T. And here's also a table that describes the continuity of the multiplication. For instance, here, this 0 here means that right multiplication with the 0 operator is SO continuous, which is obvious, of course, but it is no longer true for all orthomorphisms. So this is the minimal degree of regularity for which is still true. And here it also means that this multiplication is to-head continuous for orthomorphisms, but no longer in general for all order continuous operators. Well, this let me just flash these tables at you. For instance, we have, of course, a similar table for left multiplications, which is in the papers, and we have a similar table for multiplication on the orthomorphisms, where fortunately left and right multiplication are the same. So then we consider the matter of simultaneous multiplication, simultaneous continuity, sorry about that. Here's a sample question that you could ask yourself. Suppose that you have a strongly order convergent net S alpha and another strongly convergent net T beta. Is it then true that the product is strongly order convergent to the product? And you have 5 more of these because you have 5 more convergent structures. And here are the answers. Of course, these are the kind of optimal answers, except for the second bullet. Order convergence is always simultaneously continuous on the order continuous operators, but not on all order bounded ones. Strong order convergence always on the orthomorphisms, but not on the order bounded ones, and maybe on the order continuous ones. And for the other remaining 4, only the orthomorphisms are well behaved, and even the order continuous operators are fail to have this property. And one of the typical relevant consequences that you need when you start thinking about algebras is that if you have subalgebra of the order continuous operators, and then I don't like order closure. So then it's order adherence or order limits of method that lie in this algebra A. These also form an algebra again. And this is the kind of result that you need if you start working in this field. And we have these available now. Just to let me finish with a little more on orthomorphisms, explaining you how this why E and the orthomorphisms have the same universal completions. You take an element in your E, which generates a principal ideal. There's also a principal band corresponding to it, and there's a band projection from E onto this principal band. Now I have 2 ideals in the picture. One is in E, the principal ideal that is generated by X, and I have the principal ideal in the orthomorphisms that is generated by the projection onto this band. And the nice thing is that these 2 ideals are isomorphic, and here's an explicit formula for this isomorphism. And once you know this, you can write down 2 order dense ideals, one in E and one in the orthomorphisms of E, that are isomorphic. Namely, you take a maximal disjoint system in E, then you have all these principal ideals. You take the algebraic direct sum, and you do the same on the other side in the orthomorphisms. Then these ideals are obviously isomorphic by this proposition. And the statement is that these 2 ideals are both order dense. And it is generally known that if a vector lattice and an order dense vector sublattice have isomorphic universal completions, and when you apply this in this context, you see that E and its orthomorphisms have isomorphic universal completions. And now we can finally understand, which was the missing implication in the theorem on one of the previous slides, why E admits this desired Hausdorff-Euler-Beck topology when the orthomorphisms admit 1. So you suppose that the orthomorphisms admit it. Then you have a general fact that because this is a Dedekind complete vector lattice, so it's an order dense ideal of its universal completion. And there's a standard procedure to produce a toe-head topology on the superlattice from a toe-head topology on an order dense ideal, and this applies here. So we turn the crank and we conclude that this universal completion of the orthomorphisms also admits this desired toe-head. But we know that these two universal completions are isomorphic, so the universal completion of E also admits this toe-head topology, and then E is an ideal of its universal completion. So in particular, it is a regular sublattice, and then it's again a general fact that you can restrict this toe-head topology from EU to E to find a toe-head topology on E. So this finally
sorry, Prof. Your time is up.
Can
you? Thank you.
I'm finishing. Let me just include some references in the video and maybe in the slides if they are posted. And let me finish by just I want to read this to you, but just putting this on the screen, some nice results that we found during the process, which may help you recover from all these tables and lists that were in my talk. Thank you.
Thank you very much, Professor de Jeu. Does anyone have questions? Okay. Everybody is very quiet. Are there no questions at all? Okay. If there are no questions, thank you very much, Professor de Jeu, for your very nice presentation. And
sorry, I have a question.
Oh, there we go. Sorry, Professor Azuzi, please go ahead.
Because I hadn't managed my microphone, so thank you for the talk. I want to ask about UO-Lebesgue topology.
Mm-hmm.
If the space is not didacant complete, so there is different kinds of order convergence, and I ask about is it depending of the definition of order convergence?
You mean if you take the same index set or not?
Yeah.
I have always read these papers when you take different index sets in the definition of order convergence. I think this is a safe way to proceed. I think that most people who have been working on this UO convergence and these toe-head topologies use that convention. I hope this answers your question.
Sorry, I didn't listen very well. It depends or not?
I cannot hear you properly. I'm sorry, I can't hear you very well.
So Professor Azuzi asked if the space is not delicate complete. So UO convergence and order convergence may be different, and there are also types of UO convergence.
Yeah, you're looking at bounded. In the definition of UO convergence is point in terms of order bounded of order convergence of order bounded nets. So for it doesn't matter what definition you take with different index sets or not.
I have one question.
Yeah, sorry, yeah.
Hello. So the last theorem on the screen, it says if T from A to the order bounded operator on E is positive linear map such that TE equal to the identity operator, then the image of T stayed in the automorphism of E. Is that possible that, is that also true if TE just less equal than the identity operator?
No, we use that it's actually mapped onto the identity operator.
Okay.
No, this is really should be a uniform map.
Thank you, Professor. Any more questions? No more questions? Or do we have more questions?
Just if there is some norms on the spaces, so there is more kind of convergence.
Yeah.
Is that studied?
Yeah, that is something which is still on our to-do list, is to extend the tables even further, to include the implications where the space is a non-free space, or even a band of letters, or maybe an E-order continuous band of letters, and see what happens then. But the tables get larger and larger, so we're already satisfied that we could solve these. Because finding the counterexamples is the difficult part, actually. You just have to write them down to validate the zeros in the tables is also a non-trivial matter, not just validating the ones.
Okay.
I hope this answers the question.
Just the last question. Is the idea of convergence structure that Ian talked about, is it helpful in your work to highlight situation?
No, for us, convergence structure is just a way of being able to speak about this in a more or less precise way. We always have very specific convergence structures in mind, say order convergence or UO convergence, and these will be very nice ones. So the general theory is beautiful in itself, but for us we have very specific ones, and that's enough for us.
Okay, thank you.
Great, excellent. Thank you very much. Any more questions? If not, thank you very much, Professor de Jeu, for your nice presentation. And we look forward to the second part of your work with your students after lunch. So this concludes this morning's session. Thank you very much, everybody, for attending. And